All right, part C, we are faced with the question, for the time interval 0 to 40, must the particle change direction in any of the subintervals indicated by the data? If so, identify the subintervals and explain your reasoning. If not, explain why not. Well, change in direction, let's forget about calculus for a second. If I'm walking, in order for me to change direction from moving forward to moving backwards, I'm going to have to stop. I'll pause even just for an instant. In that instant, my velocity will I'll have zero velocity. If I was moving forward, I have positive velocity. I'm now moving backward. I have negative velocity. It's in that instant when it changes, that's what we're interested in. So a change in direction means that my velocity changes from positive to negative, or it could happen by a change from negative to positive. Maybe I was walking backwards, and then I start walking forward. Well, where does that happen? It's possible that on the time interval 0 to 8, my velocity has changed, that I've changed direction, but I don't know that for sure. What I know is that at 0 seconds, I have a velocity of 3 meters per second. At 8 seconds, I have a velocity of 5 meters per second. We cannot guarantee a change in direction on this interval. From 8 to 20, I have a velocity of positive 5 at 8 seconds. I have a velocity of negative 10 meters per second at 20 seconds. I went from forward motion to backwards motion. I am guaranteed, absolutely guaranteed, a change in my change in direction on the interval 8, 20. So I would say 8, 20, because my velocity changes from positive to negative. You could also mention the intermediate value theorem. If you know that your function is positive at one endpoint and negative on the other endpoint, and you have a continuous function, then you absolutely must have a root at some point in between. In this case, the root would be velocity equals 0. That would help you get the change in direction. So that is one interval. Let's continue examining our intervals. From 20 to 25, I have negative velocity on both ends. From 25 to 32, negative velocity on both ends. No guarantee of a change in direction. From 32 to 40, there it is again. I can see that at 32 seconds, I have negative velocity. At 40 seconds, I have positive velocity. I'd say on the interval 32 to 40, because my velocity changes from negative to positive. And that sums up your answer to this question. And that was worth 2 points. All right, last one. This one is actually I believe it was a 3-point question. I might be wrong. So we are told, suppose that the acceleration of the particle is positive. So we've got that. The acceleration of the particle is positive for the time interval 0 to 8 seconds. We then have to explain why the position of the particle at t equals 8 seconds. We need to show that the position of the particle at 8 must be greater than 30 meters. We're going to have to state that. We're going to have a logical explanation for why. We can't just say yes, we can't just say no. We're going to have to defend our answer. Well, we've just been given a lot of information. We know that the acceleration is positive. A couple of ways we can think about this. If my acceleration is positive on the interval 0 to 8, that's another way of saying that my velocity is increasing from t equals 0 to t equals 8. In fact, it's strictly increasing. My acceleration is positive for the whole time. My velocity will be increasing the whole time. Let's see how that might be helpful. We're told early in the problem that at time 0, the velocity of the particle is 3 meters per second. And that after 8 seconds, the velocity of the particle is 5 meters per second. We don't really know the values anywhere in between here, but we do know that the velocity, and this is a time versus velocity graph is increasing. So no matter what happens, I need to show, or I'm going to see, an increase in my velocity. Okay? That's going to be helpful. If I want to find the position at 8 seconds, well, the only position that I know for sure is I know my initial position. I know x of 0. I'm going to get my position at 8 seconds by starting my position at 0 seconds, and I'm going to add on to that my displacement from 0 to 8, which is the integral of the velocity from 0 to 8. It's this piece over here. First of all, this is the result of applying your fundamental theorem of calculus. But it's this piece over here that we're going to pay careful attention to. We're asking for the integral of the velocity. Another way to say that, go to your velocity curve. Find the area under the curve. Since we know that the velocity is increasing, if I look on the interval 0 to 8, so here is t equals 0, here's t equals 8. If I want to approximate this area, I can for sure, I can guarantee using the left endpoint method that this point right here, 0, 3, is actually the smallest value. So the area of this section, this little rectangle, is 24. Now how much area have I missed? I don't know. I just know I have some positive area. So what that tells me is that my position at 8 is my initial position, which is 7, plus 24, plus some more. Now, that's really bad notation for right now, but just go with me. We know it's 7 plus 24 plus some more. Okay. 7 plus 24, we know that's going to be 31. 31 plus some more must actually be greater than 30. I don't think that is a valid proof. You probably won't get the one extra point here, but let's just look at this. We know for sure that the true velocity, or I'm sorry, the area underneath the velocity curve from 0 to 8, we know that this is going to be greater than 24, which means that if I add 7 onto both sides, that inequality is still true. 7 plus the area must be greater than 31, which tells me then that this expression on the left is my position at 8 seconds. This expression on the right, if my position at 8 seconds is greater than 31, then it also must be true that it's greater than 30. And that concludes part D. Okay. So let's look at our second AP question. This question was on the 2008 AP exam. It's question number 4. No access to a calculator for this question. Let's get ourselves acquainted with the problem. We're told that a particle moves along the x-axis so that its velocity at time t, for 0 less than or equal to t less than or equal to 6, is given by a differentiable function. Differentiable function means no sharp points. Means that the function is continuous, means that we can take a derivative, all of that. It's got all the things that we would want. The graph is shown at the right. The velocity is going to be 0 at time 0. So let me make that really, really clear. I have a root over here at 0. I have a root over here at 3. And another root over here at 5. The graph has horizontal tangents at t equals 1 and t equals 4. So I'm going to have a horizontal tangent. The slope of my tangent line is equal to 0 at 4 seconds. The slope of the tangent line is also equal to 0 at 1 second. Great. We're also told that the areas of the regions bounded by the t-axis and the graph of B on the intervals 0 to 3, 3 to 5, 5 to 6 are going to be 8, 3, and 2 respectively. All right, let's continue marking up our diagram. Let's read that again. The areas of those regions, if I look from 0 to 3, that area is 8. So I've got 8 units there. Because I'm below the t-axis in this case, my velocity will be a negative. From 3 to 5, the area is 3. I'm above the axis. We're going to make that positive. And from 5 to 6, the area is 2. So if I want to look right here, that'll have to be negative 2. All right. And lastly, at time t equals 0, the particle is at x equals negative 2. So I'm going to write my position at time 0 is equal to negative 2. I think that pretty completely takes this paragraph and moves it all over onto the diagram. We're probably not going to go back and read this again. We've marked our diagram up nicely. Now let's start attacking the question. In part A, we're going to be asked to find both the time and the position of the particle when the particle is farthest to the left, and we'll have to justify our answer. In part B, they're asking us for how many values of t between 0 and 6 is the particle at negative 8. We'll have to explain our reasoning. Part C, in the interval 2 to 3, we need to know is the speed of the particle increasing or decreasing. And then in part D, during what time intervals, if any, is the acceleration of the particle negative? Honestly, I think part A is probably going to be the most challenging one, and parts B, C, and D relatively easy in comparison. Let's get started. So part A, we want to find both the time and the position when the particle is farthest to the left. So if I want to know particle farthest to the left, well, another way you could say that is I want x of t to be the smallest. I want to know when is x of t smallest. You could say where is x of t, where does x of t have an absolute minimum? And it's really this phrase, absolute minimum, that I want us to focus on. The process for finding an absolute minimum is we first look for a relative minimum, and then we're going to check our endpoints. So we're going to have to check the position at the endpoints. The endpoints for our interval are 0 seconds and 6 seconds. We're going to need to calculate that at some point. For some of my students, I think they're being really successful. They're indicating really clearly, really early in the problem that they're going to have to check the endpoints. They know that, so they jot it down. X of 0, you're told already, is equal to negative 2. The position at 6 seconds, we're going to bring on our fundamental theorem of calculus. It's my initial position plus my displacement from 0 to 6, v of t dt. Right, we're going to come back to this later on, but at least for right now, let's jot it down as a reminder to ourselves to check the endpoints. In order to show that x has an absolute minimum, what we're going to do is we're going to first look for our candidates. We need x of t to have a relative minimum. Well, a relative minimum looks like that. I need for my function, I need for my position function to move from decreasing to increasing. If x is going to be a relative minimum, if x changes from decreasing to increasing, then that means that my velocity changes from negative to positive. I'm going to look on my graph. I only see one candidate for my velocity changing from negative to positive. That happens over here at 3 seconds. So this occurs at t equals 3 seconds. That's not your final answer. That is a candidate. That's pretty standard vocabulary on the AP exam. T equals 3 seconds is a candidate. And in fact, in the scoring guide, if you just identify that t equals 3 is your candidate, that's 1 point out of the 3. You then get the remaining points by then saying, okay, I know that there's a relative minimum at 3 seconds. I then have to go and figure out my position at my endpoint. So I'm going to find x of 0 and x of 6. I'm going to find my position at 3 seconds, which again is my fundamental theorem of calculus. I take my initial position plus the integral from 0 to 3 v of t dt. The first one is already done. The second one, I have negative 2. I'm going to add on to this the integral of my velocity from 0 to 6. So I'm going to start with negative 2. I'm going to add on this area of negative 8. I'm going to add on this area of positive 3. I'm going to add on this area of negative 2. And I'm going to reach my final answer. Negative 2 plus negative 8, I'm at negative 10. Plus 3 is negative 7. Plus negative 2, I have negative 9. So my position at 6 seconds is negative 9 meters. My position at 3 seconds, I'm going to start with my initial position, plus the integral from 0 to 3, that's an area of negative 8. Negative 2 plus negative 8 is negative 10. My final answer, I have, let's check this out. We identified a candidate. We've evaluated my position function at the candidate and the endpoints. The last thing is we need to actually answer the question. We were told to find both the time and the position when the particle is farthest to the left. Well, if the particle is farthest to the left, we need the number that is most negative, and that's going to happen right here. Your conclusion should be something to the effect of the particle is furthest to the left at 3 seconds, and the position is negative 10 meters. Some version of that, and that is a full conclusion, and now the rest of this question is relatively easy. So let's move on. Part B. For how many values of t in the time interval 0 to 6 is the particle at x equals negative 8? So I'm looking for the number of solutions for the equation x of t equals negative 8. All that we have is we have the graph of our velocity function. We also know that the position of the particle at 0 seconds is negative 2 meters, so 2 meters to the left. We could find, using your fundamental theorem of calculus, the position of the particle at 3 seconds, because we are told exactly how much area there is bounded by the t-axis of the curve from 0 to 3. So if I want to do that, it'll be negative 2 plus the integral from 0 to 3 v of t dt. That'll be negative 2 plus negative 8, which is negative 10. We then can move on, and since we know exactly how much area there is above the x-axis, we can use the fundamental theorem of calculus again to find the position of the particle at 5 seconds, which will be negative 2 plus the area from 0 to 5, v of t dt. We could also have just used the result from this part. We could have the position at 3 seconds and add on to that the integral from 3 to 5. Either way is fine. You'll have negative 2 plus negative 8 plus 3, negative 7. Additionally, we know how much area is bounded by the curve from 5 to 6. The position at 6 seconds then, let's build off of this, let's be clever. It's the position that I was at 5 seconds, plus my displacement, so my integral from 5 to 6, v of t dt, which will be negative 7 plus negative 2, so I've got negative 9. Now before we actually reach our conclusion, let's make sure that we're clear on what's happening. If I need to draw a number line, because this might be helpful, we know that if this is 0, the particle is 2 meters to the left at time 0. After 3 seconds, the particle is 10 meters to the left. After 5 seconds, we are over here at 5 seconds. And at 6 seconds, over here at negative 9. 6. The question is asking how many times were we 8 meters to the left? Well, let's map this out. if we start over here, we then moved to the left. There we go, we've crossed once to get to 3 seconds. To move to 5 seconds, we went to the right. There's a second time. And then to get to 6 seconds, we crossed that line again. We've had 3 instances when the position of the particle was 8 seconds to the left. Your conclusion will have to mention the intermediate value theorem. You can apply the intermediate value theorem to each of these intervals between time 0 and 3. The particle must have been 8 meters to the left and just state by the intermediate value theorem. Same thing from 3 to 5 and from 5 to 6. So in total you have your position has been -8 3 times. All right, part C. On to part C. On the interval 2 to 3, is the speed of the particle increasing or decreasing? I want to pay careful attention to the word speed. Speed, as we know from physics class, is the absolute value of velocity. Velocity is positive if you're moving in the forward direction. It's negative when you're moving in the backwards direction. But speed is always positive. Moving forward, moving backward, we're looking at positive values. So first of all, if I wanted to change my graph from a velocity graph to a speed graph, I have to take the absolute value. The absolute value, remember, just makes negatives into positives. So this region over here that is below the t-axis would get reflected up above the t-axis. If I look at my speed curve from 2 to 3, this is where we are, t equals 2, t equals 3, my speed as I move from left to right is decreasing. And so you just need to write that down in some way that conveys that since v is less than 0 and increasing, this would tell me that my speed, which is the absolute value, if my velocity is negative and increasing, that means it's becoming less negative as you move left to right, then the speed will actually be decreasing from 2 to 3. That's all we need to state. All right, part D. During what time intervals, if any, is the acceleration of the particle negative? So key words here, acceleration. I want to know when is the acceleration negative. If my acceleration is negative, let's stop and think about the connection. We have position, we have velocity, and we have acceleration. If you know that the acceleration is negative, so if this guy over here is less than 0, then what that tells you is that the function that came above it must be velocity is decreasing. So if acceleration is negative, velocity is decreasing. Since I do have the graph of the velocity in front of me, I can look and I can see that my velocity is decreasing from 0 until I hit this horizontal tangent at 1. And I'm increasing from 1 to 3, so I'm not interested in that. I'm increasing from 3 to 4. I'm not interested in that interval. But at 4, when I finally reach that relative maximum, from 4 until 6, my velocity is decreasing. So the final answer is your acceleration will be negative from 0 to 1 seconds and from 4 to 6 seconds. And we are done with another fabulous installment of the Calculus Video Lecture Series. Good luck on your AP exam.